And another draft physics video presentation on the subject of finger there. More wave interference stuff, but this in the context of refraction and reflections between layers, which is sort of an interesting, different version of the same thing, sort of. And it's always about phase, and phase decides whether you can put photon pieces back together again. And essentially, that's the story of photons, which I would like to discuss with somebody who knows something about the subject. Do a Skype or something. I was thinking that I've had no luck in soliciting the physics, whatever, instructors on the internet, the know-it-alls, in terms of getting any feedback at all and offering them money to debunk one of the dissidents, me. I haven't been able to get anywhere. So I was just wondering if any of you have free time and you feel like soliciting from a physicist, one of these talking head types, some sort of price list, like what they would charge to attempt to debunk a video on YouTube or a theory. Let's say they want to spend a few hours to get familiar with the work of the person. So just some sort of hourly rate thing, like what would it cost for to provoke them to engage in the process. Be nice to have a price list anyway. Because I'm probably willing to pay whatever dumbass price they ask for. That's the irony. But I just can't get the price list. Just be curious if you can get the price list, what they would charge if they don't know who it is. Just curious. Anyway, so moving on. So yes, we'll play a Van Briesen video. So might as well go over what the idea is here. Yeah, that looks alright. So when light hits a surface, the idea is some percentage of the light is reflected. Now, physics doesn't really deal with that concept because, see, I'm just going to go through some of the pieces of this where this is the evidence and this stuff we know. So what we know is if I change this distance, that is if I alter the thickness of the glass by polishing the glass, I can change this reflection rate anywhere from 0 to 16% of the light. So that's pretty dramatic, And they really don't have an explanation. They'll say, like Richard Feynman once kind of just quipped, well, what do you think? You think the bottom surface tells the top surface what to do? I mean, how does the bottom surface know how much light reflected off the top surface? Some kind of crap like that. And, it's crap. Because, in theory, the two surfaces would be communicating with each other, actually. Because there's a set number of atoms that can fit into space. And if you move one of the atoms, it can be easily understood that everybody else decides to move too. You don't get to move one of them without all the other deck chairs being rearranged. So, just a fact that it's going to affect all the other atoms, and their alignment with each other will change. And you can understand that if the alignment changes, the surface changes, and they change proportionally, blah, blah, blah. So there's a reasonable explanation for the fact. It's a fact. This is the experimental result. And they don't have any explanation for it. They just don't. So anyway, so what's happening here is if you have a really thin film, really thin substance you're going through, then you can sort of understand that the reflections end up being very tiny, and that means the light that comes in is likely to come back out again, and when it reflects off the bottom surface, very close to the light that went in, because there's not much distance to fiddle with. That's one way of looking at it. So those bits can combine to create a photon because they're occupying very close to the same amount of space. And the trick would be as their phase would be altered by this distance. And so this is, if you get into nanometer kind of distances in terms of thinness, you can have a lot of these little reflections, internal reflections, and a lot of light coming out. So part of the photons get broken. So you could argue that the photons come in as groups of stuff, and a certain percentage of the stuff gets kicked out off the first surface. So you could say that much. And then a certain more percentage gets kicked out by the bottom surface and goes through to the next surface and then reflects again. So there's all these opportunities for reflections and transmissions, but the end result is that, you know, in most of these cases, most of the light is coming back out, because what you have under here is something that either is pretty reflective percentage-wise or absorptive. I mean, you could put black stuff under here, I suppose, but if you have enough layers, you could sort of understand that just by attrition, this number, whatever it is, 8 or 16, you're going to add up those percentages, and eventually most of the light's coming back out. It just depends on where it's coming back out, you know, and what angles, and in what, you know, from what position is it going to return to the regular world. All right, now, is there anything else elemental to say? So it also has to be conceded that surfaces are tricky, because surfaces don't have a flat surface, you know, perfectly flat surface. They're made of electrons, and the electrons are spaced, obviously, because they don't like each other, so they're staggered. And so the photon that's going to hit an electron is likely to go different depths into the surface. So even a transparent surface still hits electrons fairly deep into that surface. I can't remember what, I think the average was, I mean, the best kind of surfaces, the best mirrored surfaces, the photons are still going some, you know, 16 to 20 atoms deep into the surface, some of the photons, before they hit something that causes a reflection. So they are reflecting from different depths, and the thickness of the atoms is a 0.5 nanometers, something like that, the average. So you do the math, there's 20, you might have 40 nanometers worth of extra out of phaseness. Yeah, you can see that. Just in the fact that what came in going, you know, all nicely lined up is going to cause some misalignment by the fact that one of the bits is going to hit an atom there, and one of the bits is going to hit an atom all the way down here, and that means that the two that were in alignment are now going to be out of alignment. You know, they're going to be 40 nanometers worth of wrong in terms of their ejection time. All right, so that's probably enough to start. Oh, I'll be back. I think I need a sneeze or something. All right, should be back. So the Van Briesen video. You can just kind of see from the graphic that you know, you've got layers of stuff, and it goes from part of the catch, part of the observed experimental results, is that when it goes from a less dense to a more dense surface, they apply an arbitrary, I would argue, phase shift, as if the somehow the entire, you know, half a phase, call it a phase shift because it's a half a phase, which means it ends up being destructive to the photon. Remember, if they have two of these phase shifts, you could understand that now they're sort of back on phase, because that would be a whole wavelength. And I would argue that there's no theory for the application of that, and that the actual distance is what's causing the change in any phase. So there's real causes for the phase shift. It isn't just some arbitrary thing where it hits a surface and phase shifts. Fact is, if the surface is more dense, that means the light takes longer to get through it. It doesn't travel at the speed of light. in a straight line anymore. It travels at the speed of light in a less than straight line, in the sense that the momentum is given to electrons, which move slower, and then they goes back to being a force again, then hits another electron, moves slower. So the more electrons it hits, the more delayed the progress of the photon. I don't know if I want to go into, I've already explained a lot of that, but anyway, let's play along.
Welcome to iLecture Online, and our next section, section 5, has to do with the thin film. And again, the thin film is a device, is something that causes interference of light. And let me explain just a moment how that works. So let's say we have a glass, this could be a lens, or this could be a window, or anything like that, and we put a small thin layer of some material on there that has a different index of refraction of either the air or the glass. And let's say in our example here, the index of refraction is 1.4. What that means is that when a beam of light comes to the boundary between the air and the film, part of it will be refracted and goes into the film, part of it will be reflected. Then when you get to the other side of that boundary, again, part of the light will be refracted into the glass and part of the light.
So there's the first reflection, as indicated, and then there's the going through, which is at a changed angle, but it's not terribly relevant. And then it reflects off the other surface. So the argument would be is that it's really reflecting off of the new surface. It's reflecting off the surface that it's going to that it's up against. So there's no way to say that, but air is a surface. So the thing is that for it's always, you have to take the air out between surfaces, and so this film is like a film that's attached to this one surface. So the transmission is from really it just exits one surface and just reflects off the top surface of the other surface. There's not another transition between a layer between them. So attached surfaces are different than surfaces that have any other material between them, like atmosphere. Yeah, I think I stated that clearly enough.
It will be reflected off of this boundary. And to be honest, of course, at this point, some of the light will also be reflected again, but we're going to ignore that portion of it. We're all going to take a look at the reflected light of the top of the boundary here, of the first boundary between the air and the coating, and then we're going to look at the reflected light that comes off the boundary between the coating and the glass.
So they sort of ignore two aspects. First, the polarization of the light, the fact that we can only detect light that affects a certain particular surface of a material, and it's the energy that hits that crystal, that clump of atoms, the electrons within that clump of atoms that can be detected as a single photon. You can't really see the photon if like half the photon is on one crystal and half the photon's on another crystal. Things like that will mean the photon won't be visible as a reflected photon. Let's see what else can be said about that. But yeah, you need really all of them. So they always ignore all the other reflections because they're not doing theory. They just want to do a mathematical equation. And to really understand it in theory, you have to really understand that there's a bunch of divergence in the direction that the light is actually, pieces of the light are going, and that you're recombining pieces of photons. So they only want to deal with photons from which they can say a whole photon came from, or places, and they're not recognizing that those places are just happen to be the places where a photon was reconstructed. It's not the only place that light is. Yeah, I suppose that's one way of saying it. Okay, take a little break. Alright, back, and we'll play some more such.
When those two beams come together, they can either interfere, well, they will interfere with each other, but they can either have constructive or destructive interference. In other words, if those two beams are in phase, then you'll see constructive interference and you'll see some bright light come back on the other side.
Okay, so the idea, I would argue, the counter theory is that you're not, there's no place for photons to interfere. They're little bits, little nodes of energy, however you want to understand it. It's a node, a wavelet, a piece of photon, and the pieces are what you're putting back together. So there's no constructive and destructive interference. There's just the process of taking bits that are aligned, okay, and doing two things to them, okay, knocking out pieces of the alignment. Let's see if I can draw that correctly, where now you're going to put it through a system that's going to not only change the distance between them, because say this one goes, you know, to the bottom surface, and this one reflects off the top surface, so obviously this one's well on its way, this one's going to take a while, so it's going to end up being whatever this distance is behind in terms of its wavelength, well, this plus this distance, and so it's changing its phase by a set amount of distance, but obviously if I do that to this bit and this bit and this bit, if I did the same thing to those three pieces of light, well, those three then would end up coming out back in phase, because they would all be, the distances would be back to being proportional again, because they all traveled the same, you know, extra distance. And the other thing you're doing is, yeah, so the phase is the most important. And again, a photon can only be received that has a certain amount of the width of it. It can only be received, you know, on a piece of matter. You can't spread it out like one piece of the photon is over there, one piece is over there, one over here and over here, and you get a photon back. It has to be within the limits of whatever you're going to do to receive the photon, the mechanism, the material, the device used to receive it. Is anything else on this part? But there's no, these never bang into each other, they never interfere, they never destructively anything. 2 bits don't equal 0 bits, none of that's happening. You're either, you break it by having it interact with something, and it's broken in the sense that one piece flew off of this surface, another piece flies off of this surface, and they end up flying off at different angles and from different locations. And the game is, from any one position, you'll be able to put a certain number of them back together that will also have the same phase. So, you know, one coming from over here will end up being in the right phase with one coming over here, and you'll be able to see a photon there. But you won't see it someplace else. And so this is sort of demonstrated by the fact that when you do like a 2-slit experiment, you know, and you're shining light, as you move the surface, you change the positions essentially that are light and dark. So as I move the surface in, I move the position of these light and dark spots, you know, in these directions, and as I move it out, I move the light and dark spots in these directions. So it's different places depending on where you look from. If I look at it from here, I might see nothing because the distances interfere there, but I will see it from this distance because the two are the right distances to remake the phase. So depending on how far away I move my eyes from the surface, I will see, you know, different positions will create, reconstruct photons and not reconstruct photons. Which is sort of an interesting subject, in the sense that, you know, that's a truth in the slit experiment, but in the experiment where you have well, I guess the illusion is your own eye, right? I mean, everything changes. If I move closer to the camera, the black part of the camera gets bigger, it's filling more space, you know. So once you're inside of this cone, you're okay, but well, I have to think about how to better state that. But things do change. As I move the chalk closer, more of my retina is getting hit by chalk. So obviously there's new positions where there's white, you know, where it wasn't white here. If at this distance there was places that were white when it was here, and they're not white anymore.
Excuse me, if the two beams of light are out of phase, then they will destructively interfere, and essentially you could see nothing at all. So you could actually see zero light being reflected because they're disruptive interference.
Right, so it isn't destructive, there's no interference, it's just unconstructive reconstruction. You didn't reconstruct a photon because they remain out of phase. You might have the pieces, but you have the wrong phase, or you have the right phase, but you don't have enough pieces. Those are your two reasons you won't see a photon.
Which means then that the light will be completely transmitted. So if no light is reflected, all the light is transmitted. If light is reflected, then that particular wavelength of light is not being transmitted. An interesting thing happened to us when we were driving home from my kid's soccer game. We were driving on the freeway, and I was looking on the other side, seeing all the cars coming from the opposite direction, and the sun was shining on those cars. And what was really interesting was there was a very bright blue spot on every one of the windshields, all the way down as far as the eye could see, on every one of the cars. And I go, wow, that's exactly what's going on over here. On windshields of cars, apparently, they put a very thin film, a very thin coating on the windshield that will cause blue light to be reflected.
Well, I mean, it's sort of obvious that they put more than that on windshields on the inside and out because, yes, they don't, they're tinted, they're lots of things, so they certainly don't look like regular glass.
From the windshields, and the rest of the light to be transmitted through the windshield. And why would that be? Well, there's two advantages to that. If you reflect part of the light and allow the rest of the light to come through, you'll see a crisper, sharper image. So that means you can see very clear through the windshield because there's less of a, what we would call, your eye can then better focus on the singular wavelengths that come through, except as compared to all the light coming through the windshield. And secondly, it is a little bit softer on the...
Yeah, maybe that's a scatter argument, right? The blue light is the higher frequency light, more likely to scatter after the surface, and therefore more likely to create random photons, from scattering and then reflecting off other materials and then coming in. So the windshield gets clearer because there's less light scattered in the glass. Glass doesn't really like high frequencies, so the higher the frequency, the less transparent it is, and the more it disperses the radiation. So it's dispersing blue light. That's why glass gets kind of bluish when you make it really thick. It's because it's dispersing more of the blue light than the other elements, and we already did the why that is kind of argument in the previous video, so probably won't go over that again. Yeah.
Because blue light is a little bit harsher to the eye than, of course, the yellows and orange and the red and so forth. And so then the image is a little bit softer to the eye, and it takes a little bit of the intensity of the light.
All right, so this is very unscientific in the way he's saying it. I don't know, maybe he would like to have said the same thing, that the blue light is more disruptive and passing through the glass. It doesn't go through as even straight, and therefore it creates aberrant light, like the atmosphere glowing light. It's creating a background that makes it impossible to see into the universe and all that stuff because it's creating light from that direction, and it's really not an image of anything we want to see. We don't want to see the droplets of water in the sky. You might want to see Alpha Centauri or something, and you can't see it because there's a bunch of stupid light coming from the sun going sideways and reflecting back to your eye from a wrong location, from a not a very useful location, and therefore ruining your vision. So you could look at it as the windshield is like the atmosphere. The atmosphere diffuses blue light, and it reflects more, quote unquote. It's not the only light that's being diffused, but it's diffused in higher proportion because of the fact that it's purple light and blue light's more likely, violet light's more likely to be scattered.
Away. So all kinds of advantages, but it was kind of interesting how that worked. So here I'm going to use this as an example to show you how a thin film works like that. So in this case, we have blue light being reflected and the rest of the light coming through. And let's say that the wavelength of blue light, let's say that lambda is equal to 400 nanometers. Okay.
So his argument is that somehow blue light, because of the thin film, it's creating the same effect as dispersed atoms in atmosphere, because what's making the blue light capable of being scattered more dramatically, that is damaged more substantially, would be my argument, is the fact that the atoms are far apart, okay, and so it makes the other forms of radiation able to get through with only losing little pieces, little bits of their information. Where the blue light is, if it hits something, it's more likely to hit it a lot because it's got a tiny polarization, and its polarization allows it to hit a lot of electrons on the same atom, and therefore have most of its information going some other direction. But what the theory is here, we'll have to wait and see.
If that is the case, then how does a thin film work? Well, for one thing, you can see that there's a path length difference. The extra distance traveled by the second ray, there's the first ray, there's the second ray being reflected. You can see that it has to travel through the film and back through the film this way. And if the thickness of the film is t, then we can see that the extra distance traveled is equal to 2 times the thickness of the film. Now, for the light to be reflected, these two have to be in phase.
That's pretty simple, okay? It takes a certain amount of distance to go in and then a certain amount of distance to go out. 2t, okay? That one's not complicated.
Which means that the extra distance traveled must equal a full wavelength. If they're equal to a full wavelength, then of course they will be back in phase and there'll be constructed interference. But we have to...
Okay, so we're back to the back in phase argument, in the sense that I would argue it's back in phase is critically important, but you're really putting pieces back in phase. So there'll be specific positions, okay, where different frequency light can be put back together, and obviously that position shifts for the wider wavelengths. But there's nothing yet indicating that thin film can discriminate between red light and blue light, do something different to blue light than it's doing to the red light. Because again, the light is just this. Whether it's blue or red or any color, okay, this is what hits electrons, this stuff. And it doesn't know, before it left, what this frequency is, right? It doesn't know whether it's, big frequency, red light, or whether it's blue light here, this little frequency. It can't tell the difference when it's this bit is going to hit an electron. It's going to hit an electron, it's going to move the electron into a new location, and by doing that, the electron is going to be in a new position, interact with the universe, and the universe is going to readmit the photon in the fact that the position has changed, and now it's sending energy from a different location. This location and this location reflect the universe differently and create a different pattern in the universe. So it's just duplicating the pattern by moving electrons. But anyway, the key point is that the actual bits of red and blue light are identical. So there's nothing about their interaction. They're all interacting at the speed of light. They're all just a quanta. So if you really believe in this quantum mechanics stuff, there's no intrinsic difference between a red and a blue quanta of energy. It can only know the difference based on the timing of how it's getting hit, and that is if it gets hit by more than one, before an electron gets back to its position, it gets hit again. That kind of argument. That's the only thing it can detect, and that's how we detect a photon. Is that enough photons are thrown at a location to hit electrons more than once, and by hitting them more than once, you create electricity.
Be careful here. Since the light is traveling through a coating that has an index of refraction that's different from air, the wavelength will have shrunk. There'll be a smaller wavelength, so the extra distance traveled is equal to lambda sub n, which means it's equal to the wavelength in air.
All right, so this is another thing where they give Volkswagen's wavelength. They're always playing around with this stuff. So the truth is that the photon goes through the material in more time. It takes more time to get through it. But they have no proof that has anything to do with the wavelength of the light actually changing. The wavelength doesn't change because they know that when it gets out of the material, it's going back to its old wavelength. So the wavelength doesn't change. All that you've done is you've taken the speed of light force, converted it into motion by an electron that's a lot slower than the speed of light, and then convert that back into force again, moving the speed of light. And because it took time to do that, all right, it had nothing to do with changing the wavelength of the energy at all.
Divided by the index of refraction of that coating, and so we're going to use n equals 1.4 in here to adjust for the wavelength. And so we can now say that if the extra distance traveled, which is equal to lambda over n, if the extra distance traveled by the second ray, which is lambda over n, is equal to twice the thickness of the film, then we'll have constructive interference. And now the question comes in, how thick do they need to make the film to make that happen? Well, we're looking for T.
Right, so it's always going to be proportional to the distance. So the time is all you're saying. Saying how thick does the film have to be? That is, how many electrons am I likely to hit? You know, the thicker I make the material, the more electrons I'm going to hit, likely to hit. And you're just saying how many electrons does it take to slow it down enough, right, for it to be the right amount out of phase. That's it.
So we can say that lambda is equal to 2t times n, or in this case, t is equal to lambda divided by 2n, and the wavelength we're trying to get to be reflected is going to be 400 nanometers. That's 400 times 10 to the minus 9 meters, and we divide that by 2 times n, and n of the coating is 1.4, and yep, that's it. And so where's my calculator? Here we go. So we take 400 e to the 9 minus, divide by 2, divided by 1.4. That means we have to have a coating.
So again, the coating doesn't really explain how it's differentiating between, you know, red light and blue light. It doesn't say, oh, this thick coating will somehow trap more red light, or trap more blue light, or cause a reflection of more red light, or cause a reflection of more blue light. So that's the part they don't explain anywhere that I've seen.
That has a thickness of 143 nanometers. Now that's not a lot. That's a very thin coating, and you could probably look at the glass and not really see it, but it's there. They put that on there, and something like that will allow the blue light to be reflected off windshields and the rest of the light to be transmitted through the windshields. So very clever invention. Now,
more likely, the truth is that it's scattering all the light, and the only light you're going to see back in a coherent reflection is the blue light. But you've already broken a lot of the red light too. You just can't put the pieces back together because the amount of they're out of phase can't be turned into a full wavelength for red light. It ends up being a quarter or an eighth or some other stupid number. So you would need like 16 reflections to be able to get it back on phase again. So therefore you don't see much of it because not too many of them not too many of the pieces can restore the outcome. And it's more likely that the film contains more than just a film, that it contains tiny little bits of crap that ends up scattering the blue light. So the film isn't discriminating. The film is only making it possible for you to see more blue light, but for it to filter more blue light, it has to have a certain makeup, a certain particulates in it that ends up scattering more of the blue light, that is causing more of the blue light to be deflected sideways, dispersed.
one more thing that I ignored, and we have to be careful. There's something else that happens at the boundary of light when it gets reflected. It's not something we have to worry about when it's transmitted or refracted, but when it's reflected, something may happen to the light. When light bounces off a boundary or reflects off a boundary, where the index of refraction on the other side of the boundary is greater than the index of refraction where it came from, then light will actually have a phase shift, an instantaneous shift of 180 degrees.
Right. So there's absolutely no reasonable explanation for that. And clearly it doesn't go with the physics at all. Like I said, it doesn't go with even the concession they'll make that the surface itself isn't a flat surface, that even on the best reflective surfaces, you're changing how deep you go into the material with each reflection a little bit. So why would there be some automatic rule that somehow you're a phase, one complete wavelength or 1/2 wavelength phase shift? So the phase shift is 1/2 of a wavelength. So if this was the this is the wavelength going in, this half wavelength is what it comes out. And so they've just made this rule because it's just a fact that when you do all these transmission angles, when you do all of this distance math, reflecting off top surfaces, then bottom surface, then you could argue the next surface that's next to that surface, and so on and so on. It turns out that you can use this shortcut of just doing this phase shift on reflection, but you kind of know that there has to be a transmission before you get the phase shift. You don't get a phase shift off any surface. You get a phase shift off going through the surface and hitting, it's hitting a surface, and this is a real distance, not a fake distance. But they just say anything that's destructive, that is when you don't put the photons back together, they just say that's automatically 180 degrees. So any phase shift, so it could be a 50 degree phase shift or a 170 degree phase shift, and they don't care, they'll just call it a 180 because, or it could be a 250. Anything that's not 300 multiples of 360 degrees, all right, that's outside the boundaries of the error margin. So you're just really saying when you're going to remake the photon, how much can they be off? Say it's 500 nanometer light. I mean, can this be 490 nanometers, and can this be through 520? How much can the distance be off the phase and still be seen as a photon? And so the destructive part is the fact that if it's off phase enough, you won't see it, even if it has all the pieces. If they're in the wrong order, I mean they have the wrong distances between them, you won't see it as a photon. All right. But I've been over all that. So finish up.
So here I'm going to put the letter yes, or Y for yes, because yes, there is a phase shift here because we go from 1 to 1.4, which means the light, as it's reflected, is already 180 degrees different from what it was when it bounced out of the interface. On the second interface, we also have a condition where the index of refraction on the other side, the dot for a glass, is greater than the index of refraction of the coating. So there's going to be a phase shift as well. And if there's a phase shift at both boundaries, then we can simply ignore it and follow this rule and nothing has happened. But what if one of these has no phase shift and the other one does? That means the two rays already are 180 degrees out of phase without having to travel an extra distance. And there's going to be an example next when we...
But that's the whole point. They will travel extra distance because one will go back through and reflect, and that's the one you're going to reconstruct. So when they do, like I said, they're just doing this because they're not doing the path of all the rays. Because it's the ray that really does transmit. You have to really go through the material to get a phase shift. You don't get a phase shift for nothing. And so that's the part that's just wrong. There's no phase shift in a perfect reflection. Just isn't. Just isn't. Yeah. Well, let me just think about that for a minute, right? Because the trick is, let's see how it would work. Because you are moving an electron, and the electron will move the same distance in and out. So if you're just thought of it as you're hitting something with a little ball, and this ball will move, and then move, it'll be on a spring. All right, so you're going to hit it, right? So it compresses the spring, it moves into the spring, and stops. So it's in a new position. It's lower. So if something else was to hit it, it would be reflecting off a lower position. And then the other thing it's going to do is the spring is now going to push it back. So it stopped it, now it's going to push it back in the other direction. And so it's going to regain its original position. So in a sense, that would be this velocity down into the spring would represent, it would compress as quickly as it decompresses. So in a sense, you could say that would be the phase shift, because the time it takes to compress will be the same amount of time it takes to uncompress, and that would be the wavelength of the light. So the bit hit here, there's the process of compression and then decompression, and then it's released at this later point. So this reflection takes place when it hits. There's a reflection, so that's this bit leaves this way, ends up in this position when this bit ends up creating the next node. So I guess it's possible, but yeah, I'll have to think about it some more. It's all how you understand how the photon is created. Like I said, they don't have any explanation for what creates the photon, from one surface to the other, what it transitions into, and then what actually creates what we see as a photon. And what I'm arguing is what we're seeing is just like if you were shooting me with bullets constantly that just bounced right back off of me. You'd understand that if I move my hand out, the bullets would be bouncing off sooner. You get them back a lot sooner with something I stick in front of you than if you wait for them to do this. So whatever pattern I create, you'll see it in your bullets, right? So if your bullets just come, randomly and densely enough, whatever movement I make will allow you to see whatever movement I'm making in the bullets that return to you. So if you understand, that's what these electrons are doing. They're moving, and by moving, they're changing their position, which takes the pattern that went in. So if you're shooting bullets at me and you stop shooting them, you're shooting them all randomly except a very few of them, 10 of them out of a million. You shoot with some pattern, at a precise pattern. You could sort of understand that that precise pattern will dent me, and I'll throw it back at you. And you'll get that pattern back. It'll reflect, because everything's reflecting. But if I change the position, as you shoot the pattern and I put something that has a slant to it, then I'll ruin your pattern. Because now it won't be coming off a flat surface. It'll be coming off a broken surface, and now the phase, the pattern that you sent, will be completely broken because one bit of it will fly off much earlier and another bit will fly off much later, and your pattern is going to be annihilated by the pattern of my surface. It's it's like those tools. You can use a tool that has a bunch of wires in it, and you press it against something and it mimics whatever the surface looks like, and you just have to think of that in motion. And that's just going back and forth all the time between everything in the universe, is communicating its surface. It's showing its surface to everybody else, and that's why we see colors and we see all this stuff, is because all the surfaces are different, and the different surfaces are letting us know they're different surfaces. Because we send a consistent pattern in, they give us a different pattern back. Or they filtered pattern. Only part of what we send, like with red, blue, green light, only part of what we send comes back. And that's why we see things as green, red, and blue, is because part of the pattern is being absorbed, disrupted by surface irregularities, and other parts aren't. And one of the irregularities, as stated, is little tiny objects in the way will filter the high frequency light, the high frequency patterns, the patterns that are in a very narrow range, and the patterns that are in a bigger range are a lot more durable in getting through little tiny filters. It's like shooting bullets at dinosaurs, right? It doesn't do much because it's hard to hit anything meaningful, right? See, I don't know. There's probably a better way to say that. I won't bother trying. I've already explained it once or twice, and that's probably enough.
Continue with this topic on how to deal with it when these two are not the same. So before you complete the problem, before you figure out what the thickness of the coating should be, always take a look and make sure that there's whether or not there are phase differences caused by the reflection of the light, if the index of refraction is greater on the other side compared to where you came from.
So again, his argument is that thin films are blocking more blue light. They're not by nature. Okay, what they will do is send back the light in a different location than the other colors. And if you want the film to really filter, you have to put something else in it.
If it's yes here and yes there, or if it's no here and no there, then you don't need to worry about it like in this particular example. But if it's yes here and no, or no and yes, if they're different, then you do have to take into account, and the next example will show you how to do that.
Right. So all you're really doing is creating an upper atmosphere, okay, that ends up absorbing the blue light, sending it sideways, and eventually that way or that way, from a different location. And it's less disturbing, okay, to vision because you've diffused it and you've broken it besides. And by doing that, less of the photons are going to end up getting to you. But you have to have something in the film. If you just use a white, clear film, this isn't going to work. So, he's implying you can just use a clear film and your problem is solved, and that's all you need to do. And all that'll do is, like I said, the blue light's going to reflect back more parallel, so it's definitely going to head for you more often because it's not going to go through the internal reflections. It'll go through them at much higher angles. But it's not going to solve the problem of, it's not going to disperse the blue light. Okay. Enough said, I think. So again, so we're to the point where there's just, we've got enough evidence to, provoke a challenge to conventional physics, and it's just getting them to man up and demonstrate how these simple answers can't be the right answer. And they can't do it because the theory they already have has gaping unexplained events in it. Obvious unexplained events. It just phase shift 180 degrees. We say so. No explanation of why it's so. Alright, till next time and such. So forth and whatnot. Did do a live room just to see what would happen. It crashed after about 15 minutes. The video quality is kind of sucks, so probably won't do that. So if I'm going to talk to somebody, I'll probably do it through Skype and just record it because it's much better quality that way. So anyway, till the next time.